So here the problem is saying that we have a binary string containing only 0 and 1. We can perform this following operation. Okay. The operation is that we pick any index and then flip the binary character in it. Okay, so if it was 0, it becomes 1, and vice versa. And then it states that the string is called good if it doesn't contain 010 or 101. Okay, as any subsequence. So it doesn't contain 0, then other binary characters, then 1, then other binary characters, then 0. Okay, we'll make an observation about this. So we want to make the string good with the minimum number of operations. So make the minimum number of flips to make this string good. Okay, and here's the input. We are given t number of test cases and the size of the string, which is 1000. So a hint here is that this should be solved in of n. Okay, because 100 times 1000 equals 10 power 5. That's enough. We cannot do it in like of n squared or something. Okay. Okay, let's go ahead. I think you can see my screen on Visual Studio Code now, right? Okay. So let's make the following observations about the string being good. So we want to make it good, but what's meant by good? So the string shouldn't have shouldn't have 010 or 101 as a subsequence. Subsequence means that it shouldn't have 010 as any element as this order in the string. So if we have a string like this, so it's clearly not good because we have 010 here and 010 here. Okay. So subsequence means that if we have a string like this, so there is any binary characters here. Okay, these dots may be empty. Okay, and this may be ones or zeros. So we shouldn't have this form: 0, then 1, then 0, then 1, then 0, then 1. Okay. So what comes to mind now is a good string should only be something like this, or okay, so it should have only zeros and then ones, or only ones and then zeros. Okay, so this is a different string. Okay, so this is only the good string. Okay, so by definition of the string not being good here, we concluded that this only should be the good string, or so something like this, or something like this. So we could have these zeros as an empty substring, or we could have these ones as an empty. Okay, so these are only the 4 types. So we shouldn't have one after ones before zeros, and we shouldn't have zeros after zeros before ones. Okay, so this only is the good string. So how could we form this good string with the minimum number of flips possible? So let's think. I will make this greater to make you. Okay, I think this is better now. Okay. So, so here if we have any string, let's see how could we make it a good one. So we have only four forms. of a good string, right? So we want to make either all of these ones and all of any substring ones, so of any size, any substring of one, then immediately after it zeros, or zeros and then ones, or it could be all zeros and it could be all ones. So it makes sense to just try them all. So it's fairly simple. We will loop from the first index, and then we will store two sums. So some of the left ones and some of the right ones. Okay. So we'll have left, right. So we'll have some for for the current index. So if we are at index I, we will have some for the left ones. So the total number of ones before I, and the total number of ones after I. And then now we know how many ones we have after this index and how many ones before this index, and how many operations required to change these ones. Okay, so if we, let's make this smaller. Okay, so if we divided this, so if we are at index 2 here, okay, so actually make left equal sum until I, right equal sum after I. Okay, so sum of ones until I, and here sum of ones after I. So if you are here at an index 2, right, or zero based index 1, okay, so we'll have left equals 1 and right equals 2, right? So because we have one ones before this and two ones, okay, so here we'll have 1 2, okay, so this is left and this is right. So how do you think we can change this string into good? Given so how many operations we would do to change this string is to good? Actually, uh, there are two cases. So we either change all these ones to zeros and change all these zeros to ones. So this will cost us 3, right? So we change all these ones to zeros. So it will cost us 2, uh, 2 for the right, plus change all these ones, all these zeros to ones, okay? So this will cost us 1. Or we would change all these to ones and all these to zeros. Also, this will cost us 2 plus 1, okay? So that's only the case. So if we are at any index, we want to know how many operations we will do to change the right part into zeros and the left part into ones, or how many operations should we do to change the right part into ones and the left into zeros. That's it. Okay. To make things easier, so left and right with sum of ones is enough. But to make things easier, let's make another two left and right for zeros that store the number of zero sums. Okay. So let's then left 0, right 0, and here left 1, right 1. Okay. So this will be very easier now. So if we have we are maintaining now 4 variables. Everyone is storing, so we have everything is stored. Everyone is storing the sum of the zeros and the ones on the left and on the right. Okay. So here this is ones if we are staying at this index. Okay. If we are staying at this index. So this is ones, and this is zeros. 1 1, right? Because we have 1 0 here and 1 0 here. Okay. So actually the answer will be the minimum between those. So the answer will be min. So either change these ones to zeros and then change these zeros to ones, so it will be either it's 1 plus 1, or change these ones at the right to zeros and change these zeros at the left to 1, so this 3. So we take this with this or this with this because it's reverse, right? So the answer will be the minimum between this, which is 2. Okay, so let's jump back to the code and see how could we make that. Okay, so we start with taking the input.
Just one question: how you are separating it to left, right? Like first two are on leftmost and next three
Can,
on right.
can you raise your voice? I cannot hear you clearly. Can you raise it?
Yeah.
Okay.
How you dividing that string into two parts on 29 line number, 0 1 and left 0 1 as leftmost and remaining as rightmost, like how you are dividing?
Okay, so here, so I'll make it in the code, but how am I dividing? I am looping through every index from I, so I'm looping through every I from 0 until n. Okay, so if I equals to 0, then I know that the left means the ones, the left means starting from I until 0, and the right starting from I plus 1 until n minus 1. Okay, so if here I said that I divide this, so I didn't literally divide it. I am here standing at I equals 1. Okay, so here at I equals 1, actually 0 based index. Okay, so at I equals 1, I know that I'm calculating the left, taking I with me, so from I equals 1, and the right from after me. Okay, so the right starting from index 2. Okay, can you get this?
Okay, okay.
Okay, so we will
Um,
loop through every hour. Okay, so
Hi.
here we're.
Hello.
Hello, yes. Do you have
Yeah,
any?
I'm relatively new over here. I just had a small doubt. You said that it has to be done in big of n, right? But here I'm seeing like for this, whatever we're doing, it may take n square, right? Because one loop for traversing to the index and the other loop for knowing the left and right most, right? Am I correct?
Yes. So actually, I wanted to take your ideas. So it's good that you are thinking with
Okay,
me.
okay, okay,
Um, but as I said here, we now want to solve it in of n only.
okay,
Okay. So we will try to make this.
okay,
We'll try to calculate the left and right parts while looping. Okay. So while looping through every index, I try to calculate this. How could we make this? We could make it with prefix and suffix array. So let's make it simple. So we
okay,
will start if we started at index 0. Actually, I'll go to the code and then explain it. Okay.
okay, sure.
Okay. So we'll take the test cases first. Okay. So we'll make four integers here, as you said. So left one, right one, left 0, right 0, left 0, left one, right 0, right one. Okay. So to give you how could we make this approach, it it was something called moving window or something like this. So okay, so if we have something like this, and we are standing at this index, okay, so index number 0. So we want to know. Let's make it another index. We are standing at index number 2. Okay. So we want to update every I we are moving to. We want to update these four variables. And one can see that these variables could be updated easily if we have the right part and the left part, right? Because if we have, for example, left equals 3, right equals 4, Okay, so this is make it left one, right one. So it's clear to see that if we pass this I, so if we are at I equals 3, for example, so at I equals to 4, we will just increase this by 1 and decrease this by 1 if and only if we are standing at a 1, right? Because so if s of I equals to 1 and then I increased I, so at I equals 3, we were having this, okay? So at I equals 4, actually I found a new one. Then I will be increasing left one by 1, right? And then decreasing right one by 1. So just make this plus plus right minus minus. Okay, did you get this? I think it's simple. We will code it and it will be easier. Okay. Um, okay. So since we are starting from the first index, which is 0, I want to make this array one based index array. So I will make this string larger by 2 just to have space. I'll tell you why now. Okay. So let's make it. So here, n equals to s dot size. This is the size of the string. Okay. Um, so then I will increase it by 2 just to have extra space at the right and extra space at the left, because I'll start before the first index and end after the last index, just to calculate this case where I have all ones and all zeros. Okay. So here character, let's call it B for the binary string. So I will fill this character array with this binary string, but starting from index 1, okay, until index n. So actually I don't have to make it character, I will make it bool, because it's only 0 and 1. So for car cfs, or I'll make it for int I. Minus 2 I plus plus. Or actually I'll make it as the size. So here, if I'm standing at an index 0, so I want to fill the next index of binary, because I'm shifting everyone by the right one. So I'm starting from index 1. Okay, so I'll make bin of I plus 1 equals s of I. But s of I is character, right? And here I'm storing a boolean. So I'll make it s of I equals 1. So what does that do is if s of I equals to 1, so these conditions returns 1, right, which is true. So here it's stored 1. If it equals to 0, then it returns false. So here it returns 0. Okay. I think so. Okay. So to calculate. Okay. Do you have any questions?
Plus one, I think.
Any questions?
Oh yeah, why we were taking bin of I plus one for s of I? That's one I do.
Okay. So here the string is something like this. This is the string starting from index 0, 0 based index. But here I want to shift everything by 1 to make it one based index. Okay, so because I'll start uh, from index 0 and then take all the string to the right. Okay, so what does that mean? If is that this equals to 5. So I want to make another this boolean array is the same thing as this, but having extra spaces at the end. Why is that? First, to make it one based index. Second, because if we are looping through every I to calculate the left part and the right part, we want at some point, if you are standing at the most right part and the most left part, we want to take the whole string with us. So if we didn't make this, we will always be dividing this string into two parts, right? So we will always be dividing it into two parts and then calculating ones for the right and ones for the left and so on. But we now forgot about the case where we have only ones and only zeros. So this only to ensure that we will not only be dividing the string into two parts, but we will also divide it into a whole part. Okay, did you get me? So
Okay.
just to make it one based index. Okay, so that's it.
Arman,
So
how can we calculate the right part? Like for the left part, we can calculate it in the flow. Like within the loop, we can calculate. That how can we pre-calculate that right part?
yes, so now you knew how we calculate the left part. So actually, it's easy to calculate the right part before actually entering the loop. So before anything, let's take this string again. Before anything, we have the right before entering the loop. We have the right here equals to all the total number of ones in the binary string, right? And then the right zero equals the total number of zeros in the whole string. That's before entering the loop at the very first index, right? So we will just calculate the right part for the zero and one before entering and calculating the left part. Okay, so it could be done with a simple loop here. Actually, from one bar. So here we just make right one plus equal. So here we just add to right one. No, I have binary here. Okay. So here I just added bin of I. So if it's okay. So if it's one, I just add one to the right one. If it's zero, I just add one to right zero. What's this? And I equals to zero. Okay. So now for this loop, for this entire loop, I'm just calculating the left part and the right part before starting to calculate the left parts. Okay. So this right one zero right one, this is calculating after we end this loop. These have all the number of ones in the string, and these have all the number of zeros. Okay, and all the number of zeros. And initially, this should be equals to zero, so the left parts should be equals to zero. We don't have anything else. And then after we increase every I, we will change this. Okay, it's simple. So here, let's do it and start the second loop for calculating the I. So here we'll start from zero, okay? Because we want to take this empty part as because the right part will be also considered. Okay. I have one thing. Actually, we don't want to add this empty part at the end, okay? Because we'll just consider the whole string once, okay? So it doesn't make sense to calculate the whole string twice. Just consider it once, okay? So we'll make this size minus one, okay? Okay. So here it comes of calculating the left and right, as I said here. So if bin I equal one, so if it equals to one, then I'll decrease left one, I'll increase left one by one, and decrease right one by one. So right one by one, right one plus plus. Okay. There is a thing here. If you are at zero, we will not make this, okay? Because if we are at 0, this is not uh, an actual part of the string, okay? So if we are not at 0, we'll calculate this. So if I greater than 0, then we'll calculate the right and the left parts, okay? So else, so if it's 1, we'll just uh, we'll just increase the left by 1 and decrease the right by 1. If it's 0, then we'll increase the left 0 by 1 and decrease the right 0 by 1. Okay, so that's it. So after making left and right parts okay, now here it comes to calculating the answer for every I, right? So here we want to choose the maximum answer for every I. So we'll store here an integer answer equals to 0, which is the minimum thing. Okay. Actually, we want to store it a very big thing because we'll be minimizing this answer as we are going through the string. Okay, so we'll make it a very big thing, like 29, 10 power 9. Okay, so here it is just ans equals minimum ans, so we'll be minimizing answer. Okay, so it will be the minimum between left 1 plus right 0, because so we'll take reverse, so left 1 plus right 0, or left 0 plus right 1. Okay, so what does that mean? So left 0 plus right 1 means that we will flip all the left zeros, all the left ones to zeros, okay, and flip all the right zeros to ones. So here is one part, or we flip all the left zeros to ones and all the right ones to zeros, and that's it. Okay, do anyone have any question for this? So actually we finished, so this is the answer. So all the calculation is happening here. All the calculations are happening here. Okay. So of course, for the part where I equals to 0, it won't enter here. So it will calculate uh, ants from the first time, um, and these will be equals to 0. Okay. So it will just calculate the whole string the first time. Okay. Let's check. Okay. Okay. Everything should be okay.
In the second loop, why are we giving that I is less than or equal to n? It will not overflow there.
Why are we looping until n?
Less than or equal to n. Yeah, so n is the maximum size which we have given for the generator.
Mm, so we shifted the string to be one based index. Okay. Yes, n is n plus 1. Yes, you're right. So it will be s dot size, or I is more than n. Yes, you're right. Okay. Um, yes. It should be okay. Okay, we'll try it now. So there is an overflow on that. Oh yes, we should initialize this with 0. So at first initialize everything with 0, and then we calculate everything from the beginning. Okay. 0, 0, 1, 1, 0, 0, 2. 0, 0, 1, 1, 0, 0, 2. Okay, so this should be okay. I'll submit it, of course. But do you have any question? for this code for submitting? Do you all understand every part? I guess yes. Okay. Let's check it first. Okay, accepted. So let's jump. I'll give you the link here. So here's the link to the first problem. Let's jump to the second problem. So open this problem, second problem here, D. So it's this joint set of common divisors. The link here, I sent it after the first problem. Open it and have 2-3 minutes to think about it, and then tell me. Okay.
How are you getting input to this problem?
For which problem?
Like for the previous problem, it was from the terminal you are getting input. So then,
The codeforces problem?
no, your local one. You ran that program, and where was the input given to that?
So I didn't get your question. So here's the code. What's your question?
Yeah, you coded
So
on. Yeah, right. So you're getting it from the terminal, but where was it given? You didn't provide any input.
your voice is not so clear, so I don't get you. But I got that you are asking about my input. So I'm getting where I'm getting the input from this IDE.
Yes.
Yes. So this is Visual Studio Code has an integrated terminal. So here this is an integrated terminal, and I'm just writing the input here. Okay.
Oh, okay. Okay.
That's it. Okay.
The second problem was disjoint set of common divisors, right?
Uh, what did you say?
Problem.
So for the second problem, what was you saying?
What was the second problem? Actually, the title.
So here's the second problem. I'll send the link again. But we don't want to send many links just to don't make everything. Okay, so here's the second problem. It's at coder. Okay, it's on at coder site. So open the second problem, read it carefully. Okay, I think we must have finished reading the problem. Any ideas how to solve this problem? Just speak if you have any ideas. Did you actually finish reading the problem? Anyone speak?
Yes.
Okay. If anyone have any ideas, let's speak to make things interactive. Okay, let's explain the statement first. So you are given two integers, two positive integers, and the constraints for them are until 10 power 12. Okay, you're given two positive integers, and we will choose some positive common divisors of a and b. Okay, so we will get divisors of a, divisors of b, and we will choose some of the common divisors. Okay, some of the divisors that are present in both of them. And then we want to choose all of these common divisors such that they are all co-prime. Okay, so any of these two should be co-prime. What does that co-prime mean? Co-prime means that they don't have any common divisor except one. So do you know GCD? So what GCD means? GCD means it's an abbreviation for greater common divisor. Okay. So GCD 6.3. So the greatest GCD 6.3 means the greatest common divisor. So greatest GCD 6.3 means the greatest common divisor between 6 and 3. And here we clearly see that it's 3. Okay. So the greatest common divisor between 6 and 3 is 3. And for 6 and 4, it's 2. Okay. So 2 divides both 4 and 6. Okay, so here what the statement says is that it will give us A and B. Okay, it will give us A and B, and then we want to choose some common divisors of them such that the GCD between any pair of these common divisors should be 1. So if we choose like A1, D1, D2, D3. So these, let's say that these are the common divisors we chose uh, between A and B. Okay, they could be all the common divisors or just some of them. So let's take an example. So if we have A equals to 10, let's make it 12. Uh, B equals 10, 20. Okay. So the divisors for 12, let's see them, is 1, 2, 3. So here the divisors for 12, it's 1, 2, 3, 4, 6, 12. Okay. These are the divisors for 12. And these are the divisors for 20. 1, 2, 4, 5. What else? That's it. 10, 20. Okay, so these are the divisors for 12, and these are the divisors of 20. Okay, so we will only consider the common divisors. So 12 is not common, so we'll remove it. Okay, 6 is not common because it's not there, so we'll remove it. And then 20 is not common between these, so we'll remove it. And then 10 is not common, so we'll also remove it. 5 is not common, we'll remove it. 4 is common, we'll keep it. 2 is common, keep it. 3 is not common, remove it. And then 1 is common, keep it. So we ended up at only 1, 2, 4. So these are the only common divisors, okay? Common divisors. These are the only common divisors between 12 and 20 as we saw now. So what does the problem say is that after getting these common divisors, we want to choose some of them. It doesn't matter how many or something. We want to choose some of them such that um, the GCD between every pair is 1. So GCD between any pair. So GCD between 1 and 4 should be 1, 1 and 2 should be 1, 4 and 2 should be 1, and so on. Okay, so we want to choose as many as possible, as many common divisors as possible, such that the GCD between any pair is 1. Okay. Here we see that if we choose, so here any two chosen divisor must be coprime. So coprime means that the GCD is 1. Okay, so coprime GCD means that coprime means that the GCD equals to 1. So here to satisfy this condition, it's clear that we cannot choose these three common divisors because the GCD between this pair is not 1. GCD between 2 and 4 is 2, actually. Okay. Okay. So we will remove one of them. Like we'll remove 4. Okay. So this for these two is enough. So the answer for this problem for this input, which is 12 and 20, should be 2. So he wants us to output at most how many divisors can we choose. So the at most means the maximum number of common divisors we can choose such that they are all coprime. So for this input, we'll print 2. That's it. Okay.
Yeah, we can also choose 1 and 4 so that it becomes 3, right?
No, actually, you should. So if you choose 1 and 2, this will only be will also be 2. So we are not counting the number of pairs. We are counting the maximum number of common divisors we can choose at only one step. So we want to choose the maximum number of common divisors such that they satisfy the condition that they are all coprime. Okay? Can you get it? Uh, okay, I didn't hear you, but okay. Um, okay, so anyone have any ideas how to solve this? How to get the maximum number of common divisors? How to choose the maximum number of common divisors such that they are all coprime? Any ideas? Just say any ideas. What complexity should we solve it in? No one wanna talk? Okay, so one hint is that this input is very large, right? So it's until 10 power 12. So it's clear that we cannot do it in of n. Okay, so it cannot be done in big O of n. But it can be done in big O of square root n. So at least square root n, at most, okay, square root n. So we cannot do anything slower than square root n because square root 10 power 12 would be 10 power 6. So at most, we can make it complexity of square root n. And this is the desired complexity that will be solving this problem in. Okay. Mm, okay, so let's jump ahead to the solution. So first, do you know how to get, so let's make it simple. First, do you know how to get the common divisors for two numbers? So we are given A and B. How to just print the common divisors of them? Anyone know?
Yeah,
Just speak.
we divide from starting 1 to the until number. which is divisible, that one, which coefficient is 0, that one we will take into the list.
So I didn't get what you say exactly. So I loop from what to what and then check what?
One to that number, and
Okay.
we'll see when the coefficient, like
Okay.
mod operation. The coefficient
Okay.
is
So we're saying we loop from 1 until that number. So which number, A or B?
for each number we have to loop.
Okay. So after looping for A and for B, how could we choose the common divisors? So
No,
so now we made.
have two lists. So
Okay.
we'll be having two lists with common divisors of 12 and 24, and we compare and bring it to one list. Then we will out of them we will choose which is a co-prime
Okay.
number.
Okay. I got it.
That's it.
So you're saying we loop from 1 to A, and then the same thing for B.
Uh, or else we can loop for the smallest number.
Smallest number? Yes, you are right. So I was
Yeah.
going to say that. So I don't have to look for after the smallest number because there are no common divisors after the smallest number, after the greatest number, after the smallest, of course. Okay. So it will be until mean A and B. So why should I make two lists? So actually, I should only check for every number inside one loop.
Yeah,
So yes, so I
yeah,
don't
but
have to make two lists, right? Okay.
yes, you're correct.
Okay, so so if we made this for this problem, it should take off n, right? And this is too slow, of course, for these constraints, which is 10 power 12. This is 10 power 12. Okay, so so if we made this approach, this will be 10 power 12. Actually, you are right. This is how we are checking for the divisors, but this is not the fastest way. Do you know how we can make this faster? It's just one trick. Can anyone say how we can do this faster?
Can we
If,
divide B to A, and if it is dividable, then we can go ahead. Otherwise, we can no need to loop.
I didn't got you exactly. So, what after dividing by what?
B2, largest to smallest we can divide, and see if both are divided by each other. Then we can go ahead for finding the coprimes. In the first case, if they are not divide with each other with any number, then we no need to proceed further. Means
Mm,
okay.
no, actually,
No. Yeah. Sorry. I was thinking it's the wrong.
okay, okay, no problem. Okay, this cannot happen. So this cannot happen because the two numbers like 12 and 20 are not divisible by each other, but they have common divisors. So one observation here is that if we want to get a divisor for any number n, if we want to get the divisors for any number n, we don't have to loop until n itself. Why is that? Let's fetch the divisors for the number n. So we'll try first 1, then 2, then 3, then 4, and so on until n, as you said, right? So this will take off n, right? But one trick here is that if we found that any number of those is divisor, so if we are fetching the divisors for n, and if we are here at say 3, okay, so if n is divisible by 3, that means that n mod 3 equals to 0, right? So if n mod 3 equals 0, then it's divisor. It's divisor. This is how we check for divisor. But if n mod 3 equals to 0, that that also implies that n over that implies that n divides 3. So n over 3 um, actually yes, so n divides 3, so that means that n mod n over 3 equals to 0 also. So why is that? It's clear here because so since n divides 3, so then n over 3 is a whole number, right? So n over 3, it will give us 3 back, right? Because n over n over 3 will just um, yes. So n over 3 will distribute this, so it will be equal n. Uh, what's this? Is so n over n over 3, it will be 3, because if you just multiplied everything by 3, if you multiplied everything by n over 3, then this times n over 3, and this will be 1, of course. Then 3 times n over 3 equals n. Okay, so that relation is true for every divisor. So if n if x is a divisor, then also n over x is a divisor. So do you all agree with this? So if x is a divisor, then n over x is a divisor. So let's take, for example, 12 or 24. So let's see the divisors. So 1 is a divisor, of course, right? But also 24 over 1 is a divisor, which is 24, right? So let's check 2. 2 is a divisor. But also 24 over 2 is a divisor, which is 12. And 3 is a divisor. But also 24 over 3 is a divisor, which is 6, 8. Right. And 4 is not divisor, I guess. No, 4 is a divisor. 4 is divisor? Yes. 4 times 6. So 4 is divisor, but also 24 over 4 is a divisor, which is 6. So that's it. 5, no. So here we checked for 5, and it's no. And then this is 5. And then we checked for 6. But here's the thing. We checked for 6, but we passed over it from the smallest number. So whatever numbers we'll check again, which is 6, 7, 8, 9, 10, 11, 12, and so on. So these we check them. So it turns out that we don't need to loop until greater than square root of n. Why is that? Because after square root of n, the first number will get bigger, and the second number will get smaller, because n over square root of n equal square root of n. So if the square root of if we pass beyond square root of n, then this number will be smaller, and it will be we passed over it again. Okay, so we don't want to pass through over a number more than one time. So it turns out that we don't want to loop until the number itself, but instead square root of the number. Okay, do you all agree with this? That for calculating the number of divisors, we will loop until only to the square root of the number. If anyone do not understand it, just say.
So it will be square root of minimum of A or B, or it's a square root of greatest number, maximum of. It should be minimum or maximum, because
Why greatest? It should be minimum, because we are so here we are making a new a new integer which equals to the minimum between a and b. Okay, that's 10 small. So we only considering x. We don't want to consider the greatest number, because there is no divisor greater than x will be common, right? So it will be square root to the minimum
Yeah.
number. Okay, and then here we'll check for every number if it's divisor or not. Okay, so here this algorithm will run in square root of n operation, which is 10 power 6, and this will be enough. Okay, this is only a part for the problem. But here, actually calculating this square root, this is a function, so it's not calculated in constant time. So this is not square root of n. This is not square root of n without any other extra operations. So we want to make this faster, such that we don't want to add any other operations like square root of n. So instead of looping, instead of writing it as square root of n, because this is a function that runs in log n, we'll multiply both sides by square root of x. Okay, so this will be x, and this will be I. So I times I is more than or equals to x. Okay, so this we are not adding any extra operations. So this is constant time. We're not calculating the square root. So we will loop until only I times I is more than or equals to x. That's it. So if I reach square root of x, then we'll get out. Okay, and then we'll check if I is divisor for a and b. But for this particular problem, fetching all the common divisors will not be efficient, because, so let's see the example here.
The multiplication is sorry to hello.
Yes, say, I'm hearing you. Yes.
Yeah, the square root you made it as a multiplication. Yeah, that's a good idea. But is there any operational load when between square root and multiplication, or it is same, right? Or computation wise?
Actually, I made that because of computation wise. The square root function would run in log n time, but all the arithmetic operations run in constant time. So this will run in constant time. Okay.
Can you repeat the last step? Square root.
Okay. So here. So you want to this step, right?
No, something I missed that. Square root will cost more operation load than
Yeah,
multiplication.
square root will work on the log n time, and this like mathematical operations, it will work on constant time. This is what I meant to say.
Yes.
Log
So
is lesser than n, right? I mean, O of n, right?
okay. So are you getting this? So we are looking until square root of x, but the square root takes log of x time. Okay. So this will add another time. So we'll just get rid of this square root function and make the multiplication, which takes constant time. Okay. So if I equals to square root of x, so if I reach square root of x, then I times I will be equals to x, then we will go out. Okay, and if it passed the square root of x, then of course a number greater than square root power 2 will be greater than x, so it will go out. Okay, are you okay with this?
Yeah.
Okay. Okay, so let's go back to our initial problem.
So we are
Yes.
storing here I values, right? And our output should be 2, right? The output should be 2.
For this?
Yeah. The
Yes.
expected output is 2.
Should be 2,
So
yes. But how we calculate this? So do you have any idea? So here we have fetched the common divisors. How we calculate it? How we calculate the maximum number of pairs such that they are co-prime?
So we have to do other operation of looping, right? 1 to 4. We check.
Okay, so I'll make things easier. Um, so a number is a co-prime with number means that they have no common divisor, and that also means that they have no common prime in its prime factorization. So 4 equals to 2 times 2. So here our divisors are 1, 2, 2 times 2. Okay. So it's clear that if we took 2 one time, then we cannot take it another time. Okay. So if we let's get rid of this example, and if we had some a and b, and then we fetched the common divisors, and then we are having here the prime factorization of these common divisors. Okay, so we have here 1, of course, 2, 2 power 3, 5, anything. Okay, 5 power 2, 7, 5. Let's sort them. Okay, so let's, after getting the common divisors of some a and b, we have here these prime these common divisors as prime factorization, with prime factorization being applied. Okay, so how do you think we could get the maximum number of them such that they are all co-prime? So if we took 5, we cannot take it again. If we took 7, we cannot take it again. If we took 2, and so on. It's simple. How can we get the maximum number? So we just want to print the maximum number. Can anyone tell that? Any ideas?
In this case, it would be 3, right? This example, the output would be 3. So,
No.
so
Why
4,
3?
4. It's 4.
4.
1 to
Yes.
7. Yeah.
Yes. So we will take 1, 2, 5, 7. That's it. Okay. So it's clear now that it doesn't matter if we got one prime of one type, then we don't to want to get again. But if we have here 5 times 7 times 3 times 11 times 13. So this is one common divisor. Okay. So what should be the answer here now? What should be the answer for this?
Just 1 and 2.
What do you say again? Sorry, what did you say?
Answer would be 1, right? Because here we can take only 1 and 2.
I didn't get you. I didn't hear you correctly. But
It's
so
7.
any such 7? Okay,
Yeah.
1, 2,
Output would be 7. 1, 2, 3, 5, 7, 11, 13.
6. Yes, so it's 7. Why? Because we have 7 prime divisors. So we cannot get a new prime divisor. Okay, so actually, and 1 should be added. And 1 is not prime, but should be added. So 1, 2, 3, 5, 7, 11, 13, and these are 7. So it turns out that the answer should be only the number of prime divisors in the common divisor. That's it. So if we made it more simple, if we have something like 2 times 3 and 2 times 5. So these are only 2 common divisors. But actually it will not be like this. So we'll make it way smaller. So it will be 2 only, then 3 only, and then 2 we have calculated, and then 5 only. Also there will be 1. So the answer should be 4 here. 1, 2, 3, 5. So how to get the prime factorization? So So to make this problem easier, we'll make a new a new number integer called x, and x will be equals to the common prime factorization. What's this? Common prime factorization. Okay, so x will be equal to the common prime factorization between x and between a and b. Okay, so let's take an example here. So if we have like the last example again, 12 and 20. So let's take only the prime factorization, not the divisors. So the prime factorization for 12, it will be 2 times 2, 12 over 2, 6 over 2 times 3. Uh, okay, so this will be 2 times 2 times 3. This is 12, right?
You can include into 1 into also. 1 into 2 into 3.
Sorry, what did you say?
For 12, you can also include 1 into 2 into 2 into 3.
So you're saying 1 times 2 times 3? Yes, so 1 is multiplied by everything, but it doesn't matter, okay? So 1 times, so 20 over 2, it will be 10 over 2, it will be 5. Okay, so for 20, this is the prime factorization. So let's get x here will be equal to the common prime factorization, okay? But actually, since we are saying prime factorization, so we'll not consider 1 here for the sake of rules, okay? So we're saying prime factorization, so not say 1. So 1 will be at the side, we'll calculate it at the end, okay? 1 will be common with all numbers. So here we have 2 times 2 times 3 and 2 times 2 times 5, which is prime factorization. So x will be equal to the common of them. So 2, we have twice here and twice here, right? So it will be 2 times 2. 3, we don't have it, so 3 we have it here, but it's not here. So we'll not add it, okay? But if you have some A and some B, something like this, 2, 2, 2, and here just 1, 2 times 3 times 7. So what should be the prime factorization? It should be, so here we have 2 one time, and here multiple times, so we'll only take it one time. And here 3, it's common, we will take it. And here 5, it's not there, we will not take it, and 7, it's not there, we will not take it. So here the answer for this particular problem is 2. So it turns out that the answer for any A and B should be the common, the number of the common prime numbers of the common prime divisors. That's it. So, and actually, we are not interested in many two. So if we have one prime number, like 2 times 2 times 2 times 2, it doesn't matter how many twos. If we have 1 2 here and 1 2 here, that's enough, right? Because it doesn't make any sense to take 2 times 2 times 2 and 2 times 2 times 2 again. So it should only be 2 and 2. Okay. Okay. So it will be the number of common prime divisors between A and B. That's it. Okay. Are you all agreeing with me? Okay, you should be
Yeah.
agreeing. Okay. So here let's go back to our calculating program. So to see the prime, the only the prime divisors for any number, can we still calculate it with this loop? Actually not. No, we cannot do that because we want to check first. So for this loop, we are checking if I is a divisor. So if x mod I equals 0, then x is divisor. X is a divisor. But if but here I'm checking only the prime divisors. So I want to check if x is a divisor and also x is a prime. but checking the prime, but checking prime number is a whole new thing that takes the computation time, it, it, it doesn't make sense to calculate primes again here, so it won't fit. Okay, so calculating prime numbers takes square root of n for every prime number, so it won't fit here to calculate for every x if it's prime or not. But there is a trick here that we can make it to only calculate, to only pass through prime i's. So we can only pass through I where I is a prime. So how could we do that? Let's say now. So if we have some number a, and then we passed through its divisors, through numbers from a until square root a. So whenever I pass through a divisor, so I passed through one, it doesn't, we don't consider one here, okay, because it's not prime, of course. Um, if a is divisible by 2, let's take a equals to 2 times 2 times 2 times 3 times 3 times 5 times 7 times 11. Okay, so this is a here. So how should we calculate the prime divisors without seeing if a number is divisor or not? It's actually simple. So the first time we pass through a divisor for a, we just divide a by this divisor. So the first time we pass through 2 here, we keep dividing a by 2 until a is not divisible by 2 anymore. Okay, so here uh, the first number we will pass through will clearly be a prime, right? Because prime is the smallest divisor. Okay, so here we found 2. 2 is the divisor of a, and then we pass again, and we found 3. So 3 uh, 3 is divisible by a, yes. So we'll keep dividing a by 3 until it's not divisible by 3 anymore, and then we add 3. So here we had 2 a divisor and 3 a divisor, right? But then we passed 4. Note, note that at the beginning a was divisible by 4, right? And at the beginning, if we were looping through this loop, eventually we will get to 4 and then calculate 4 as a divisor. But here we have eliminated all the multiples of 2. Uh, yes, all the powers of 2. So 4 is a power of 2, so it's not divisible by a because we eliminated it, we removed it. So 4 is not divisible here anymore. Okay, and then we passed through 5, and then we found that it's the divisor, so we eliminated it. Then 5a, and then 7 we eliminated it. Actually, we passed through 6, and at the first time 6 was a divisor because 2 times 3 is 6, but here it's not divisor because we're only calculating primes. So, and then we'll get to 7 eliminated, and then we'll get to 11 eliminated. So here we found the prime divisors without actually checking if this is prime or not, because note that for any number, for any number that is not prime, for any number that's not prime, it should have a prime divisor, right? So for any number that's not prime, it should have a prime divisor. So if we are here eliminating the prime divisors, then we won't pass through any number that's not prime. Okay, so the first number we pass through it and find that it's divisor, we concluded that this is a divisor. This is a prime divisor. Okay, so we just eliminate the divisors and then prove that this is a prime divisor. How can you do that here? For let's make it a loop here. So if we have n, so to know the number of divisors of prime divisors, let's make cnt equals to 0. We'll start from 2, not 1, because 1 is not a prime. More than equals plus plus. Actually, the yes, okay. So if n mod I equals to 0, then for the first time we pass through a divisor, then we know that this is prime. Okay, so we will immediately eliminate I from n. So we'll make this while n mod I equals to 0. So if it's equals to 0, while its modulo equals to 0, then n over equals I. So I eliminated I as as long as it's divisible by n. Okay, as long as it divides n. But here first we'll add cnt plus plus. Okay, so if I found a number, then I'll increase the count by 1. So that means I found a new prime. Then I'll eliminate this number. So after this operation has finished, I'll have a new number which doesn't have this prime as a divisor. So whenever I pass through another I that's divisible, it will be prime, and then I continue and so on. And after this loop, there are two cases. N might be equals to 1, or n equals to prime. Why is that? Because if initially n was 7, or something like 14, if initially uh, n equals 14, then at the first time I'll I'll eliminate 2, then I got 2 here, I'll eliminate it, so n will be equals to 7. But then I'm saying that I times I is smaller than or equals to n. So I will not reach this 7. So I'll stop at 2, at 3. Okay. So because when I equals to 3, so 3 times 3 is 9, which is greater than 7. So I'll not complete. So I'll not reach 7. Okay. So I'll not reach 5, 6, 7. So at the end, n might be 1 or prime. So if n equals to 1, then I'm done, and I've calculated all the prime divisors. But if n equals to another number which is not 1, I'm sure that it's prime, then I'll add CNT. So in CNT plus equals n greater than 1. So that's the algorithm for calculating, for efficiently calculating the prime divisors for a number. Okay. Do you all get this?
Uh,
If anyone has questions, say.
okay, you're doing operation on n is the minimum, right? Here, n
Yes,
is
I'm just doing the prime factorization thing before jumping to the answer. Okay. So
okay.
did
This
you
is
understand the prime
prime
factorization?
factorization, right? This for loop is only for prime factorization, right?
Uh, yes. So this is only prime factorization, and for this problem, I loop for the prime factors only. Yes.
Yeah, yeah.
So
Good.
I didn't take the input yet. Okay. So here I'll check the problem again. A and B. Okay. Okay. So let's remove this. Int AB. Okay. Here ans equals. So I'll initialize ans with 1 because I'm here calculating only the prime divisors, but I also want to add 1 to the answer, right? Because here I should add I should add 1 to the answer because 1 is co-prime with all the numbers. Okay, so I'll initialize ans with 1. And here, instead of CNT plus plus, ans plus plus, and here ans. We'll mix again after finishing. Okay, because there is a trick here. So I'll take A and B. And I don't have to make it n, so I'll make it, let's see, okay, okay, I'll make it n. Maybe. Okay, so here for this loop, I'm checking. Actually, I will not make it n. Okay, so I'll make it until A, and then I'll make sure that A is the smallest number, right? So I'll make if A is greater than B, then I'll swap A with B. Okay, so I'll make sure that A is smaller than B and then loop until A, which is the smallest number. Simple. Okay. So if A is greater than B, I'll swap it with B to be the smallest. Okay. So I'll loop until A only. That will make it easier in the code. So here I check if A mod I equals to 0, then I check here if B. Actually, I will add. So I'll add 1 to the answer if and only if I is divisible, if and only if B is divisible by I. Okay. So ans plus equals B mod I equals to 0. B mod I equals to 0. So if I is divisor of B, then I'll add 1 to the answer because I'm sure that it's divisible by both. It divides both. And otherwise, if it's divisible by B or not divisible by B, I'll continue doing the prime factorization for A. Okay, because I'll just remove all the primes from A to check for every prime if it's divisible by B or not. Okay, and this is not N, of course. This is A. So A mod I equals to 0. A equals to 1. Okay. So after this, we said that A should be either 1 or some prime. So I need to add 1 to the answer if A is not equals to 1, and if it's a prime divisor of B, right? So I make ans plus, yes, so ans plus equals B greater than 1 and B mod A equals to 0. Okay, so I said here that A, if it's greater than 1 and it's divisor of B, so I'm sure that it's a prime now, right? So if it's greater than 1, then it's prime. So if it's divisor of B, then I'll add 1. Okay? Are you okay with this? So that's it. That's the answer to the whole problem. And then I'll print answer. Let me check. Three. Okay. Four. Okay. 0, 1. Okay, so are you all okay with this solution? Do you want to understand anything in it? Is everything clear?
Can you just repeat that in if loop? How you come up that if loop?
Repeat the what?
If loop, if condition.
This if?
Yes, 14, line number 14, if condition.
Okay, so
You took the minimum.
A is the minimum, right?
Yes.
Now
Yes.
A is the minimum. Okay, so I'm checking now if I is divisor of A. I'm adding one to the answer only if I is also divisor of B. Are you okay with this? I'm adding 1 to the answer only if I is divisor of B. So this condition returns true, returns 1 if I is divisible
But
by B.
why we are adding this? Why we are adding this one only if B is also divisible?
Because we are only interested in common prime divisors. So we are not
Okay.
factorizing A by itself, right?
Yeah.
We are interested only in common divisors. And then we factorize A. We just divide it by this divisor because we want to make sure that the next I we reached is also prime. Okay?
Okay.
Okay. And then we added here. So do you all understand this?
Yes.
Okay. So that's it. So it's a simple code of 10 lines, but requires observations and thinking. Okay. Okay, it should be okay. Sent. So you all can see my browser, right? So you're seeing me, you're seeing @coder here, right? Or can't you see my browser? So can you see me all submitting here,
Yeah, yeah.
or okay, okay. I was making sure that the screen's shared. Okay. Actually, there is one thing before submitting that would get us wrong answer. Here A and B are until 10 power 12, right? So integer will not fit in because integer will fit like 2 times 10 power 9. Okay, so make it long. Okay, and here there is no n. Okay, and here answer is integer. It cannot reach long. And here,
Now we have to change that
I
now also. Yeah.
eh, yes. So we make it long because I times I will overflow. Okay, that's it. Let's try again. Okay. So that's it. Okay, so I can give you the link to the submission. Okay, here's the link in the chat. Okay, let's go for another problem. Okay, take this problem in the chat, read it carefully, and then tell me what have you got.
What is the next problem?
Here I sent it in the chat.
Yeah, sure.
Okay, code forces, palindromic paths. Okay, have you all read the problem?
Yes.
Okay, do you have any ideas? I think this is easier. So, do you have any ideas for this problem? How to solve it? Okay, let me explain the problem first.
Should we approach it with dynamic programming?
Sorry, I didn't hear you.
Should we approach this problem with dynamic programming?
Dynamic programming. How should we make this? How should we make it?
I'm sorry?
How should we make dynamic programming? So, how? Yeah. So, what's the dynamic programming solution for this? What's the transitions, states? So, why you said dynamic programming? Uh, okay, so
Actually, I'm not sure. I'm asking it then.
you're asking, right? Actually, any problem could be solved with multiple ways, but this for dynamic programming, it's an overkill for this problem. It's not solved by dynamic programming. It's way easier than that. So you could solve it like greedy, solve it with just thinking and observation. Okay, there is no required typical algorithm for this problem. Okay. Okay,
I understood the problem, but I didn't understood the input string that is given in the question.
okay, I'll explain it now. I'll explain it. Okay. I'm just okay. Okay, so here's the problem. So the problem gives us T, the number of test cases, and N and M. So the problem gives us a matrix of size N times M. That means it gives us a matrix with with N rows and M columns. Okay, so here gives us N rows and columns. Okay, so if n equals to 4, M equals to 2, then we will have four rows and 2 columns. So it will be something like this. So the matrix is given. The given matrix is a binary matrix. That means it only contains 0 and 1s. Okay. So at each cell of the matrix, it's either 0 or 1. 0 or 1. Okay. In 4 columns, 2 rows. And what's required is your goal is to change the values in the minimum number of cells so that every path is palindromic. So it says that where is the definition of the path? Okay, a path is called palindromic if the number in the first cell is equal to the number in the last cell, the number in the second cell is equal to the number in the second last cell. So what palindrome means? So this is a palindrome. So a palindrome means that the first element equals to the last element, second element equal to the second last, third, uh, third, and so on. Okay. So for a path, so if we have a path in this matrix, let's make it 4 by 4 matrix for easy. Okay. So here it says that if you are at any cell, we could move to the left or to the right. Okay, so if we are here, we could move here or here, and then here or here, then here or here, and then lastly here. So let's consider only one path of these paths. Like consider this path, going this and then this. So the path is starting from the first cell until the last cell. So this path, this. So we want to check if it's palindrome or not. So do you think this is palindrome or not? Of course, this is palindrome because the last if we printed this path, I'm sorry, it will be 0 1 0 0 0 1 0. So 3 1s here and then 1 1 0 0. So this path is clearly a palindrome. Okay, so you now know the definition of palindrome, right? And then the problem asks us to change the minimum number of cells, so we could flip again this 1 to 0 or this 0 to 1 and so on, like the very first problem we solved. So we could flip any number, any binary number to the opposite to achieve the minimum number possible of operations to make all the paths palindrome. So while taking any path, we should make it palindrome. So you said that we could make it. So what comes to mind at the very first time is dynamic programming, right? Comes to mind because we want to check every path, and there are exponential number of paths, right? So the number of paths are too many. They will clearly not fit in the time. We cannot pass through every path. Okay, so the number of paths is exponential. It should be like 20 power 30 times 30. So this is a very great number of paths. We cannot look through them all. But as I said, it doesn't require dynamic programming. We should observe something. We always we always need to make the last cell in any path equals to the first cell in any path, right? Let's make me share the drawing, the whiteboard. Okay, can you see the whiteboard?
Yes.
Okay. So for any metrics, initially, do anyone have any ideas how to solve this? It's a good problem. If anyone have any idea, just go ahead, tell me, help me. Okay, it seems like no ideas.
Binary search technique. It will go with the boundary conditions.
Binary search. Not quite.
Okay.
Okay. Okay, so let's make some observations. So, okay, before approaching any problem, before saying any algorithm and something like this, before saying the technique, just observe what happens. Just make that problem easier. So observe what is the nature of every path, what's the long of every path, and so on. Okay, so here we want to check. We will first check for the first. We want to make sure that the first cell of any path equals to the last cell in any path, right? But we know that a path must start from the very first cell here and end to the last cell here, right? So, okay. So a path must start from the first cell and must end at the last cell. So now we know that all the paths, so all these exponential number of paths should, for all of them, we should have this first cell equals to that last cell. That's it. Okay, that's it for the first cell and for the last cell. Okay, so we don't need to look through all the paths to just check the first cell and last cell. So we just check them. If this equals to this, we are okay. We want to make them equal. Okay, so let's check for the second cell at any path. So for the second time, okay, for the second time, for the second move, we can go this or this, right? But for the third, so okay, let's only consider the second cells for the first path. Okay, so for any path, the second move should only end at this. So the second cell for any path should only be this and this. It doesn't change. Okay, so these two cells, are the cells that are in the second path of in the second cell for any path. Okay, so let's look at the third cell for any path. So the third cell should be either this or this or this or this. So there is no other cell. There is no other cells that lie on the third cell for any path. Okay, so these are the third cells for any path. So if you continued like this, we'll find that this is number 4. Okay. And this is 5. And this is 6. And this is 7. And this is 8. Okay. This is 9. This is 10. And this is the last cell. Okay. So it's now the problem is now very easy. It's easier than before, because now we need to make the element in this cell equals to this cell, and then make all the elements in these two cells equals to all the elements in these two cells. Because any path, the second cell for any path should only be either this or this, and the last second cell should be either this or this, right? So, and also we want to make this equals to this, and this equals to this, and so on. Okay, so until we reach, I know that things got messy, but you got it. Okay, so have you got the idea? So we want to make the for every this type of for every diagonal, we want to make the first diagonal equal to the second diagonal, the second equal to the last second, and so on. Did you get this idea? So now we want to make sure, now we want to know how actually we can minimize the number of changes to make this equals to this, and this equals to this, and so on. So, do you have any question on this? Any clarification? No questions? Okay, so you tell me now how can we solve this? So like we solved a similar problem, the first problem, right? Where we are required to change the minimum number of changes to satisfy some condition. So now we want to change the minimum number of changes to satisfy the condition that this equals this equals this. So if this is 0, this should also be 0. If this is 1, 1, this should also be 1, 1, and so on. Okay. And if this is 0, 0, 0, this should be 0, 0, 0. But also this could be 0, 0, 0, 0, and so on. Okay. Do you have any ideas how to code it? How to code that? How to actually get the minimum number of operations to achieve for any binary? Let's close this drawing.
Sorry, I didn't get like here 1 1. It's a cell position, right? It will be 1 0, right? Here in the second row, 1 0 will be the position, right?
For the second row, what you want for the second row?
No. How we are checking the palindrome here? I got it. Like, I mean, you are saying this second row and must be equals to the last from the last second row. But how we are
Yes,
comparing
diagonal.
the
Diagonal.
position values, or how is it?
Okay, I'm hearing you. I'm hearing you.
Uh, because I got it like, I mean, first position will be 0 0 and the last will be 5 5, or the position will be 6 6 based on the number of rows and columns. So how we are comparing this should be a palindrome.
So you want to know how can you compare two diagonals with each other? So how can you compare the first diagonal with the last diagonal,
Like
second
for
diagonal with the
palindrome,
second?
yeah, yeah.
Yes. Okay. So if it's not about, let me get to the whiteboard again. So for
No,
that.
actually these are not the index. These are the value 0, 1, right? So am I audible?
Hmm.
Yeah, yeah.
Yes. Yes.
So what is mean to say, like if the I 0 0 index, if it is a 0, then the last index should be 0, right?
Last index should be 0.
Last in the sense, suppose we have 5 into 5 matrix.
Yes.
So 0 0 matrix value is suppose 0, then 5
Okay.
into 5 value should be 0.
Oh, okay, okay,
Okay, and
okay.
the 1 1, if it is like see index 1 and row 1 and column 1, if both
Mm-hmm.
value are 1 1, then we
Mm.
can say 4 into 4 should be 1 1,
Oh,
Yes.
okay,
Yes.
okay,
That's right.
right?
okay,
Yeah.
okay, okay.
So
Yeah.
and we need to calculate, suppose we have 1 1 index as a 1 0 and
Mm-hmm.
4 4 as a 1 0, then fine.
Okay.
Otherwise if both are not matching, then we need to do a operation, like we
Okay.
have to
Yes.
update, yeah, delete from 0 to 1. So we need to count that how many operations we are doing to make that matrix as a palindrome.
Okay. Okay.
Am I
Thanks.
correct,
Yes.
Sarma?
Yes. Yes.
Yeah,
Exactly.
yeah,
Exactly. Yes. So we want to make the minimum number of operations to achieve this. So do you know how can we
Thank you.
make how can you change these values, these binary values? How can we minimize these values? So if we have for this matrix, let's undo this. Okay. So if we have here 0 and 1, and here 1, 1 and 1. Okay.
yeah.
So what do you think should we change for these two diagonals to make them palindromic?
Palindrome. So either we have to make this as a 1, otherwise we have to make the from last side 1 0 and one value as a 1.
Uh, yes, but there is something you didn't get quite accurate. So we shouldn't make if we have this like 1 0, we shouldn't make this 1 0. We cannot do that because we could have a path like this. Sorry, we could have a path like this. Okay, so this is not palindromic because we have 0 here and 1 here, right?
Yeah,
So we
yeah.
should have this value equals to this value equals to this value equals to this value. So all the four of these should be equal, right? So
Okay,
we don't we shouldn't make 1 0 1 0. So they all should be
okay,
either all of them are ones or zeros, right? But it's clear for this simple example, we should change this 0 to 1, right?
okay.
It doesn't make sense to change all these three ones to zeros. So
Exactly.
we just okay. So we just choose the minimum number of ones or zeros. So if we have like here something here, uh, yes, here. Okay. So if we have here 0 1 1 1 1 0 0 1. So here, if you calculated the total number of ones here, it will be 5 ones, okay, and 3 zeros. So what is more optimal, to change ones to zeros or to change zeros to ones?
Change
So
0
what's
to
more optimal
1.
here? Uh, Actually, it's more optimal to change zeros to ones, right? Because they are the smallest. So it's more optimal here to change these zeros to ones. So the answer so we will add to the answer 3. Okay. So it turns out that we just want to loop through every diagonal, and then see for every diagonal and its last it's the diagonal that's at the end that meets it, and then see the minimum number of zeros or ones, and that just add them to the answer. Okay, are you all okay with this? So we'll check for every diagonal. We'll check this with this, and then add the minimum either zeros or ones, and then we'll check this with this, and then we'll check this with this, and that with that, and that with that, and obviously for the middle diagonal, if the number of diagonals are odd, then there will be a middle diagonal, right? We won't check anything for this diagonal because it doesn't matter. So for any path that pass, so for this middle diagonal, uh, for any element, it doesn't have any element meeting it. Okay, so if a palindrome of size odd, the middle element doesn't have to change anything with the palindrome. Okay. Okay, so are you okay? Are you all okay with this approach? Okay.
Yeah, yeah.
Do you know how to do this? How can you calculate this? Any ideas? We'll jump to the code now. Okay. Okay. Any ideas how can you achieve this minimum value? Or should I start directly? Okay, I'll start. If anyone have any ideas, want to ask any question, just so we'll start. I'll start
We
with
can start with two loops, one from top, one from bottom.
yes.
Top, we compare top diagonals with the bottom diagonals, and
Okay.
we see which one we need to take, 1 or 0. I mean, what's the count of the zeros and ones, and minimum of 0 and 1 we'll take, and with that number we can replace the whole diagonal, I mean diagonals, and while during that changing we can increment the number of changes.
Um, okay, yes, you're right, but this could be tricky when we code it. So we want to know the efficient way for coding it without making things too complex. So let's check every diagonal and see what's special about this diagonal. So you're saying we will pair this with this, but how could we make this with normal for loops and something like this? It should be hard. So we are starting at 0 0, ending at
Can
n
we
minus
take
1.
it in like 3 by 3 or 4 by 4 matrix? Uh, this is
Sorry,
fine.
what did you say?
3 by
Uh,
3 by 3, 4 by 4, if we take that example, it will be easier, faster to understand.
yes, okay, but it doesn't matter here for this example. Okay, so
Yeah.
I will not draw anything in this matrix. Okay, so let's observe for the diagonals that for any diagonal, let's take this diagonal for example. So let's observe that the values of the summation between the column number and the row number for every cell is the same. What does that mean? Is if we took the column number and the row number for every cell in any diagonal, so R plus C, so R plus C for any diagonal will be the same for every cell in it. So why is that? Because mm,
R plus C, can you explain again? Row plus column, is it?
yes, rows plus columns. So R plus C is the number of row plus the number of column.
Yeah,
Okay.
C plus R equal to R plus 3 from top to bottom.
Yes. Okay. So for any diagonal, R plus C is equal. Why is that? Because if you are standing here, and then if we are standing at this cell and we have some R and some C, and then we move to this cell. So this cell's R is smaller than this. So this will be R minus 1. And this will be C plus 1 because we increase the column. So if we added this, -1, we remove -1, and we'll still R plus C, okay? And if we go to this cell, it will be the same. We will decrease row by 1, increase column by 1. And this will decrease row by 1, increase column by 1. So for any diagonal, we'll have constant R plus C, okay? So that makes it way easier. Instead of looping through the matrix and making it hard, we could
Yes, sir.
loop through the cells that have the same R plus C, and then we know for sure that they are at the same diagonals, right? Okay. So let's observe that for the first diagonal, it has the smallest R plus C, the minimum R plus C. Okay. I know that the handwriting is too bad, but I code now. Okay. Uh, so for the first diagonal, it has the minimum R plus C. For the last diagonal, of course, it has the max R plus C. Okay, so here we have the minimum R plus C, here we have the maximum R plus C. So here and here. Here R plus C is increased by 1. Okay, so it's just simple observation. So here R plus C greater than 1 from the previous diagonal. And here R plus C is smaller than the diagonal after it by 1. Okay, so whenever we are passing through diagonals, R plus C is increasing until we reach the end. Okay, do you agree with this? So for any diagonal, R plus C is increasing until we reach the end. So if we fetch these diagonals and put them in an array, so let's go to the Visual Studio. So here, if we fetch all the R plus C's, we'll have an array like this. So A1, A2, A3, A4, A5. So we will have a sorted array with being the so for every element, this is R plus C for the first. So this will be 0. This will be 1, 2, 3, 4, 5 until n minus 1 plus n minus 1, which is n plus n minus 2. Okay, so for the last element in this array, we'll have n plus n minus 2 referring to the last diagonal. And this is the first diagonal, and this is the second diagonal, and so on. Okay, so we'll have, so now the problem boiled down from a matrix to just a simple array. We have made a simple array with the number of diagonals, and for every A, we'll store the number of zeros and the number of ones. So we'll have something like B1, B2, B3, B4, B5, and so on. Okay, I'll just make this. Okay. Okay, so we have here Z1 referring to the number of zeros in A1, so in the first diagonal. O1 referring to the number of ones in the first diagonal, and so on. Okay, so O is referring to the number of ones in the corresponding diagonal, and 0 to the number of 0. So to check for the minimum operations, it's just now so simple. We will move from the first element until the element in the half. So we'll move from 0 to n plus m minus 2 over 2. Okay. And then for every element, we'll check the minimum number of, we will add to the answer the minimum number of z of I plus z of n plus m minus 2 minus I. So first element, we check it with the last element. Second element, we check it with the second last element, and so on. So we'll check for z and for ones, for zeros and for ones. And then we'll take the minimum of them. Okay, because we'll take the minimum of zeros, and that means that we'll change these zeros to ones. Or actually, we'll take the minimum from those. Okay, so we'll take either we change all the zeros to ones, or we change all the ones to zeros. Okay, and that's it. Do you understand? Do you understand now? Do you have any question before jumping to code? Okay. It seems like no questions. Okay, so so it seems easy now. Do you know how could we make this? So help me. How could we code this now? How could we make it easy for coding? Okay, no segments.
So,
Let's say I'm here. I'm hearing yes.
okay. So what I understood is here you're taking the, the first, I mean, you're taking an array like from 0 to n plus m minus 2, right? So that
Yes.
array will give us that array will give us 0, 1, 0 or 1, right? That array will give us. So you have three
Yes.
arrays right here. One array is for
Yes.
storing the numbers. I mean, like index value, sorry, cell value.
Yes. The index of the diagram. Yes.
One array is to like Z1, Z2, Z3. This array is for storing minimums, right? Or row values. That,
Yes. Okay. So we could. I'll make it. I'll I'll help you with an easy code now to make things get clear. So since we want to have two arrays, one storing 0 and one storing ones, and we are saying that this A1, A2, we're saying that we're starting from 0 until m plus n minus 2. So why don't we make an array of size m plus n minus 2, okay? And then the index of any element of the array contains the number of zeros and the number of ones for this particular diagram. So what does that mean? Is we have something like, so we take n first. So we have an array called CNT, which is count. Let's make it count. So CNT of size n plus n minus 2.
here,
Okay.
t is the size of the array, right? T.
Sorry,
What
what do you
is
say?
what is t here?
What
T.
is what?
T. T.
T.
T.
T is the number of test cases. So I'm just taking the input here,
Oh,
the
okay.
number of test cases. Okay. Okay. So here I'm starting to solve from n. Okay. So here I'm making an array of size. I'll make actually a 2D array of size n plus n minus 2, and for every cell, I'll store. I'll have I'll have two elements, the number of zeros and the number of ones. Okay, and it's just that simple. I initialize it with 0, of course. So if I, for example, access count of 0. So count of 0 will be equals to the number of zeros in the very first diagonal. Okay, and if I access count of n plus m, so actually I'll make this greater because I want to access n plus m minus 2. Okay. So if I access n plus m minus 2 of 1, for example, so this equals to the number of funds in the last cell. Okay, in the last diagonal. Okay, so it's that simple. Do you all agree with me? Okay, it seems like yes. So now we want to initialize. Now we want to actually fill this array. So first we'll take the input matrix. So we will the matrix will have n rows and m columns. So we'll make a nested loop that goes n times m times. So now we are looping, making n times m operation, and then I'm taking a boolean, a binary number. Okay. Okay. So if b is 1, then I want to increase count of I plus j. So I plus j, so I is the row number and j is the column number. So I'm accessing the diagonal of I plus j. Okay. So I plus j of b plus plus. That's it. You get it? So I'm accessing the index of the diagonal I plus j, and then whatever b is. So if b is 0, so I'm adding 1 to zeros. If b is 1, so I'm adding 1 to the number of ones. Okay. Actually, that's it. It's not that hard. Um, so for the second thing, after filling this count array, we want to actually loop, like we said, until half of the array, exactly half, to check everyone with its corresponding cell. Every diagonal with its corresponding diagonal, and then take the minimum. So we make here answer equals to 0, initialized answer, so no changes are made. And then, so we are starting from 0 until m plus n minus 1. Then that means we are yes, so enter equals 0 أصغر من n plus n minus 1. So أصغر so smaller than n plus n minus 1. So it's n plus n minus 2, right? But we want to divide this by 2 because we'll go until exactly the half of the array. Okay. Plus plus. So here we'll just add to the answer ans plus equals minimum between count of I of 0 plus count of n plus n minus 2 minus I of 0. So I'm taking the 0 part, I'm taking the number of zeros in these two diagonals, the corresponding diagonals, or the number of ones. Count I from count n plus n minus 2 minus I of 1. And that's it. So that's how we calculated the answer. Okay. And here we output the answer, and that's it. Okay. Okay. So do you have any question for this code before submitting? Anything you don't understand? Any line?
Yeah,
Yes.
can you explain me, like, a little bit confusing here? Like, the first two for loops are to
So
increase
sorry.
the,
Can you repeat again? Your voice is not clear.
uh, Ahmad, what the first for loops, two for loops are there, right? The
Yes.
first two for loops.
Actually, I'm taking an input of n times m, of size n times m. So I cannot make anything faster than this. So I'm taking every cell from the matrix. So so this is not computing anything. I'm just taking the input. Okay. So this nested loops for the input. So I cannot
Oh,
make anything faster than this. Okay. So the real computing part is here. and here is the number of the diagonals, okay, which is m plus m minus 1, which is at most 60 or 58.
So the answer is
But
like you're adding a minimum of uh, count of the first and last diagonals, comma the count of
yes,
um,
the count of 0 and the count of 1 for every corresponding diagonal. So this is the first with the last, and then the second with the second last, and so on. Okay, so here is the simple math. So n plus m minus 2 minus I. So if I is 0, then m plus m minus 2 minus 0 will be the last one. Okay, but if I is 1, then m plus m minus 2 minus 1 will be the second last one. So a simple math here, if we just made it on our head with the first two diagonals, it will be okay. Okay.
yeah, but okay, minimum of okay, got it.
No,
Got it?
minimum of in the sense like if there are zero value as a minimum, so we'll have to count that how many zeros, minimum zeros are there, or how many minimum ones are there. So it will give that count. So we'll add two answers. So these many changes is required to make that matrix as a palindrome path.
Uh, yes, I didn't hear you well, but I think you are saying correct thing. Yes, so I'm counting the number of zeros and the number of ones for every corresponding. Okay, I'm then taking the minimum. So let's try this for the example.
But the
So
question
zeros.
is number of 1, comma 1.
The question is what?
They said okay, in the question there is a chip called 1, comma 1, and it is, so they are saying like the chip is moving from top to bottom. They're not saying that taking the minimum of 0 and 1 and replace the diagonals, which is the minimum, right? It should be 1 always.
No, no, no. Actually, it won't. It is the problem. Just asks to make a path palindromic. So it doesn't matter if we change it. So here is an example matrix. Here is an example output. This is the correct output for the last case. So it doesn't matter if if these are zeros or ones, because so for these second cells, these are zeros and these are zeros. So it's palindromic. It's always palindromic. So it doesn't want us to make these ones. Okay,
Okay.
just
Okay.
just wants it to be palindromic. Okay.
Okay.
Okay, let's submit. Okay, 0344. Okay. Okay, I'll submit now. Okay, accept. Okay. Okay, so today we finished 4 problems. I guess 3 problems. So I give you one homework problem, or I'll give you 2 homework problems, just to make sure you solve them, just understand them well, and then we'll discuss them the next time. Okay, and try hard in them. Don't give up if they are hard or easy, depending on your level. So they could be easy for someone and they could be hard for someone. So try them hard and don't give up. Okay. So I'll get the problem now.
Can you share the link for that submit code submission?
Oh yes, yes. Okay. Okay, I'll send. Here's the link for the submission in the chat, and I'll give you the homework problem now. Just stay 10 seconds. Okay, here is the first problem. Sorry, the internet is slow, so I'm getting the second problem. Stay with me. Okay, I'm getting it. Okay. Okay, here's the second problem. So as I said, be sure to try them hard, and then we'll discuss them the next time. Okay. Do anyone have any question before I leave? Want to say something? Okay, that's it. Okay, bye.
Bye.
Thanks, Amit.
Bye.
Thank you for your time.
Thanks, everyone. Thanks a lot.
Okay, bye. Good luck.
Thank you.
Hello. Hello. Jitendra?
Hello. Yes, it is.
Yeah, do we have Prakar class today? 12, that is advanced data structures. Yesterday it happened.
That's at 12:30, correct. Yeah.
No, is it there today?
Yeah, correct. It's there. Yeah.
Okay, 12:30 p.m., right?
12:30 p.m. Same link. Yesterday's link will work.
Okay, fine.
I'll post again in WhatsApp group.
Regarding?
I mean, same link and
Okay,
same
okay.
message
Sure.
for today's session.
Yeah, okay.
Thank you.
Thank you.